right, so today will be the last lecture. I added a couple slides to this lecture packet. So the first slide that I added just tried to clarify the self-attention idea and the keys, queries, and values. So this was the original equation that we saw for self-attention in its simplest form. And we have, for the ith output, we can see that this is a linear combination of all the different inputs. And the combining weights are softmax versions of these inner products. And so basically for each y, x is used 3 different times. And each usage is a bit different. And then this picture is what I added. This might help to understand a little bit more about the 3 usages. So here, when we're focusing on the second y, these are the weights, and they're multiplying. These are the values. So these are the values, v. And then when you compute these weights, you can see that for y2, you're always using x2 in this position, but you're using a different version of x in this position. So this one here is the query, I believe, yeah, the query. This is the key, and then this is the value. So those are the 3 ways that these vectors are coming together, and maybe this picture helps explain that idea. Okay, any questions on this picture? Okay, and then what we said is what's actually done is you put a matrix multiply here, here, and here, and you learn those matrices. And so that's, here are those matrix multiplies. And then you have self-attention with a scaling factor to make the softmax work better. And then from there, we said you do one final thing where you actually split those matrices into a certain number of parts, and you do self-attention separately on each part with a unique combination of matrices. And that gives us multi-headed self-attention. Okay. And then we saw that those self-attention blocks are combined with layer norm and 2-layer MLPs and skip connections to create a transformer block. And then those transformer blocks are cascaded to form the actual, full network, the full model. And then we saw one way of how this model can be used, and today we'll see another way. But in this on this slide, we're using this transformer model to do classification. And in particular, we have a sentence coming in, like a movie review, and we're trying to predict whether it's a positive or a negative review. And so one thing we had to do is we had to add positional encoding or embedding that tells the transformer this is the first word in the sentence, this is the second, this is the third, this is the fourth, and so on. Otherwise, everything else that we're doing here is permutation equivariant, meaning you could shuffle the order of these words and the output wouldn't change, and that would be a bad thing because obviously the order of the word matters. So the positional embedding is used to sort of train the transformer to be sensitive to the word order here. And then the other thing we do for classification is we have this output sequence, again, of some tokens which represent words. And what we can do is we can just average them across time, and then that vector, this is the time average vector here, we can just convert that into a K-class representation that is trying to predict the one hot coded label. And so that final, we need a matrix here that converts from dimension D to dimension K. We can add a bias too. And then that is also trained in conjunction with all the transformers, weight matrices for this classification task. So this is how we can use a transformer for classification. Okay, so we talked about how we do the positional encoding. We talked a bit how we do tokenization. Tokenization is sort of a two-step process, or tokenization is one step, embedding is the second step. So in tokenization, you convert text to integers. And there's various ways to do this. Sometimes you convert a character, each character to an integer. Sometimes you convert a piece of a word, like walk or ing, you convert those to integers. Otherwise, it might be a piece of a sentence. There's various approaches. But in any case, from this tokenization step, you now have a sequence of integers. And those integers still need to be converted to real vectors, which are called the embeddings. And to do that, you basically design a codebook, and then you use the value of this integer, this token, to just extract a particular column from that codebook, and that becomes the input. So that's how we go from the tokens to the embeddings. And now, once this stuff goes through the transformer, and we get an output sequence here, these are all embeddings from our codebook, but this is not guaranteed to be in the codebook. It's probably some linear combination of codebook words. So to figure out, which code words it is closest to, you can train this one-layer network with a softmax here to give you a probability distribution. And so the largest entry in this gives you the probability of the most likely code word. So that's unembedding, is instead of going to a specific code word, you could, if you just looked at the maximum index in here, or you could say, well, I have several possibilities. It could be this word, or it could be this token, it could be this token, and so on, and now we have a PMF over those tokens. Okay. So that's tokenization and embedding for text. Any questions on that? We'll see some examples today of what these numbers end up being, like how big is the code book, how long are the embeddings, and all that. And then if we're working with images, we can do that too. We can use transformers for images. Then it's a natural question of how you actually do that embedding. And a simple thing we can do is we can break the image into small, like 16 by 16 patches, and then basically code them directly into embeddings. There's really no, in this case, there would be no tokenization, no integer quantities that are associated with the patches. However, you can get integer quantities associated with patches if you quantize, if you put a quantization step in the middle, and that's one of the things that's done in this vector quantization VAE approach. Okay, so you can basically work with images too, and then you can also work jointly with text and images by coming up with some embedding space that merges the information from text and images. And those methods are used when you have like a text to image generator. We'll talk about some of those, or even image to text, or for multimodal models that work on text and images all together. Okay, so I think that's what we did last time. Are there any questions on anything from last time? Okay, so let's now talk a little bit more about large language models and text generation. And so this would be another task that you could use with these transformer blocks. And so this task is called next token prediction. So basically, you have this transformer, which is a cascade of transformer blocks. And the way that, and here you can see we have our input sequence, we have the embeddings, we have the positional encoding in two. And we're basically training the transformer to predict a left shift of the input. So if the input is HELL, those characters, we are predicting it to, make the word hello. So it shifts these guys left, this one falls off, and then we're saying predict the O. And the reason it's called autoregressive is if you keep doing this over and over and over, you can generate long strings of text. And so a few details on that. Remember that this transformer is a sequence-to-sequence predictor. So you start with this, so this is how you train it, this is the target, but in reality, it may give you something very different than this. So like, for example, maybe you give it HELL, and it predicts elbow, right? Where it's maybe, correctly predicted the O that you were hoping for, but it's also changed this L to a B. Okay, so what you actually do then is you ignore all this stuff. You only use the last predicted token, and you concatenate that with the last inputs to make the next input. And then you feed this in over here and so on. So it's like you only use the last generated output. You kind of ignore these and you fill them with those values. So that's how this stuff is run at inference. Okay, any questions on that idea? So that's kind of the idea driving a lot of these current large language models is this task. I'll explain a little bit more about why that is in a moment, but now there is a kind of a critical issue here that if we were not careful, this stack of transformers could learn to just copy this to this without really understanding the meaning and the structure of this sentence or this word. And we don't want it to just copy. I mean, in some sense, yes, that would, if our goal was only to predict this next character or next token, yes, but really the goal in training these is really for it to understand the structure of language, the meaning of this. Only when it really understands language is it going to, give like human-like performance and really be able to generalize to new tasks that it hasn't been trained on. So the key is to not let it cheat, to not let it just copy. And to do that, there's something called masked self-attention. So the idea behind masked self-attention is, so this is what we saw before for our basic self-attention layer, but now we're going to stick in this masking matrix that has zeros in the bottom left triangle, but the upper right triangle has minus infinities. And if you remember, when you put a minus infinity into a softmax, that goes way to the left and it basically gives you zero output. So that's forcing a certain structure. In particular, as a result, the first output, y1, which is this, is basically these things force it to ignore all the values of the input except for the first input. So the first output can only depend on the first input. So basically here, it is trying to predict E knowing only H. And then the second output can depend on the first two inputs through this. And so basically here that's saying it's trying to predict L based on HE and so on. And finally, the very last one can use all the inputs. So the last Y gets to use them all. So basically what this means is you're kind of training the model to do many tasks in parallel. You're training it to predict E from H and L from HE and this other L from HEL and O from HELL. You're doing that all at the same time which is a lot more powerful than just basically training it to do this and copying that. Okay, so this is the idea behind masked self-attention, and it's a key idea in these autoregressive transformers. All right, any questions on masked self-attention? No? Everybody good? Okay. All right, so now we'll start talking about sort of history, and I'll show you how transformers evolved over time, and we'll get into some numbers and everything. So the very first transformer, well, I guess this is the paper that people refer to as the first transformer, although if you look back in time, you can find ideas that are similar that go all the way back, I think, even to the 80s maybe. But this was really the one that started a revolution. It's from Google in June 2017. The paper is called "Attention is All You Need," where they kind of they described this attention mechanism, and they basically said this is really all you need to train a network. You don't need to have a bunch of other stuff there too. Attention is everything. And then they also proposed an architecture that's very similar to what's still being used today, and similar to what I showed you earlier in these notes. But the overall structure of the network was a bit different. And to understand that, we have to understand that the focus of this method was really language translation. So going, let's say, from, I don't know, maybe Spanish to English. And so the architecture actually had two different transformers. One on the left is the encoder, the one on the right is the decoder. And the job of the encoder, and maybe we should even change this, maybe I'll do HOLA. So that's Spanish for hello. And so the job of the encoder is to take in the entire context and understand, what does this mean? And code that in its own kind of internal language, which is this latent vector. So it's basically taking this information and summarizing the meaning of that sentence or word or whatever as this. And then the decoder is the autoregressive text generation that we just described. It is going to focus on English text because we're translating Spanish to English, and it's going to be driven by that latent vector. So the latent vector is basically telling it, generate a sentence with the same meaning as this sentence, or in this case, this part of a word. And then it's doing that autoregressive text generation that we just described. So given this input, we're training it to predict this output. But then at inference, it might mess things up. We ignore these. We basically take this, and we combine those and set that as the new input, and we just generate, gradually we generate, the words, the characters in this word or the words in the sentence, or how we broke things up into tokens. Okay, so it has this encoder, joint encoder-decoder architecture. But it turns out that this architecture was kind of abandoned by later models. This was something that only showed up very early on. And later people realized that it's enough to either just train a decoder for some applications or just train an encoder for other applications. And so, to my understanding, people are not building things this way anymore. They've simplified it. Question?
What is the size of the latent vector?
I don't remember, in this paper, what it is, but it just needs to be large enough that it captures the information in this sentence or whatever that is.
Does it depend on the code book or the input sequence?
I mean, this length is fixed, this length is fixed, this dimension is fixed. So, I don't know what they ended up using, but yeah, I'm sure if you wanted to know, you could look in the paper, it probably says. Yeah, I just don't remember what that is. Like I said, this is not an architecture that's really used anymore, so I didn't pay too much attention to the details. Okay. And there's another trick they had. So when training the decoder, they couldn't use the autoregressive stuff because, so they use a trick called teacher forcing. And the idea is when training, let's say, you know this is the English word, and then this is the left shift. So maybe during training, the decoder messes up, all these characters. And then if you really did at training use this messed up character with this, you would have the wrong thing at the next training step. So instead, it basically just uses this as a target. You get whatever predictions of these, and you ignore them. And then at the input, this is the teacher forcing. You just you force the input to be disconnected from the output. You just force it to be the training inputs. You don't actually feed anything back during training. Only during test do you actually start feeding things back. Okay. All right, so that's the original transformer. Any questions? Okay. So GPT-1, released by OpenAI in June 2018. So one of the key words here is pre-trained. That's the PT, generative pre-trained transformer. And so the significance of that is that at the time when they were working on this, most of these natural language processing models, they were trained using, in a supervised manner, using labeled data, meaning, I guess it's going to depend on the task. So like maybe if you're training for movie rating prediction, you have a movie rating, you have a movie review, you have maybe a rating that's a number of stars, and you want to try to predict the number of stars using the text. So just various tasks where you need supervised training. You need a label in addition to the text. But there's really not that much data out there like that. However, as we know, there's tons of just text data in the world and on the internet. So that was their idea. So they proposed to what they call pre-train on this next token prediction, which is an unsupervised task because you're just predicting the next word in a sequence of words that you know. So there's really no need for labels. It's sort of, the labels are already there. And then, once you pre-train this transformer and it kind of understands the generic structure of language and so on, then you fine-tune it on a desired task, which might be classification or whatever you want it to do. And that is something we learned as transfer learning back in Unit 9. So in a convolutional network, you train all the convolutional layers, and then maybe you retrain just the dense layer. And here it's sort of often similar. They might just take off the last transformer block and then retrain a new one. So the training is really broken into these two stages. There's the pre-training, where they give it tons and tons of text, and it takes a long time, very expensive. But then the fine-tuning is usually much cheaper, and it's something they do many times for different applications and so on. Okay, so any questions on the idea of pre-training and fine-tuning? Okay. All right, so this GPT-1 used byte pair encoding, so that's how it did the tokenization. So basically it's just, I believe, just characters, and the number of tokens is 50,000. So that's data point. It's a decoder-only model because it's trained for next token prediction. That's exactly just this stuff, but even without this latent part. And it has 12 transformer blocks. It has 12 attention heads per block. It has an embedding dimension of 768, context length of 512 tokens, and 117 million parameters. So for that pre-training, the data they used was the book corpus dataset, which contained 7,000 unpublished fiction books, a total of about 1 billion words. And the total amount of training compute is often described in kind of a strange way. So the way this is petaflops per second is kind of like a computing speed. And then you multiply that by the number of days you ran at petaflops per second. and in total you get compute. You could represent this number in petaflops alone and get rid of seconds per days if you just multiply this number by the number of seconds in a day. So then you could just give that number petaflops. For some reason, that's not how these things are reported. I don't know why, but these things are reported this way, and then the numbers, have a different meaning. So this is petaflops per second times days. Anyway, and this at the time cost about $50,000 to train this model. All right, so that's the first GPT. Any questions? All right, so this model I think was partially successful, but just a little bit later, so that was June, this is October 2018, Google released their bidirectional encoder representation from transformers, and this made a splash because I think it worked a lot better than GPT-1, and it's sort of like the first model that people really thought, wow, this is starting to get human-like. Now, interestingly, the key idea here, is bidirectional. So whereas GPT was basically only predicting the last character, always predicting to the right, BERT is not doing that. It's actually an encoder-only model. That's why it's bidirectional. And it's predicting a random masked word in a sentence. So, like in this case, I guess in this case here, it would be like taking hola, the word, and then randomly masking one of these characters out, and then asking this model, can you predict what that character is? Of course, this is a toy example, so it could be randomly masked word. That was one of the things, and that masking could be anywhere. And so it had to kind of understand everything in order to be able to predict a masked word anywhere. And then it had another task. It was whether one 256-word sentence follows another or not. So for that, it really has to understand the meaning of an entire sentence to be able to distinguish whether one sentence follows another or not. So those are the two ideas. Still was, unsupervised. And then the final layer is replaced, and the model is fine-tuned for a specific task. This one used word piece tokenization with a vocabulary size of 30,000. It used 24 transformer blocks, 16 attention heads per block, embedding dimension of 1024, context length of 512, and 340 million parameters. So you can see the model is growing, 117 to 340. Context is getting longer. Well, no, context is the same. Embedding dimension got a little bit larger. For pre-training, they used 800 million words from English books and 2.5 billion words from English Wikipedia articles, 250 billion tokens total. And this took 6 petaflop per second days and cost about 7,000. So what's interesting is you notice that the compute went from 1 to 6, but the cost went from 50,000 down to 7,000. And this is just because somehow at the time, maybe NVIDIA released a new GPU, or somehow the costs for training came down. And so they were able to train with more compute for less cost. Okay, so that's BERT. And BERT is actually still used today. It's still referred to a lot. It's still a pretty famous model. Okay, any questions? All right. Okay, so GPT-2. So this was released in February 2019 as an improvement of GPT-1, and is very similar training procedure, very similar architecture. One thing they changed is the layer norm was moved from after the transformer to the front, or I guess after the self-attention layer to before, and after the MLPs to before. and that improved the train stability. But other than that, I think everything was pretty much the same. It was a kind of a new modification of BPE tokenization, a similar vocabulary size to before, but now you can see it's deeper, 48 transformer blocks, 25 attention heads per block. The embedding dimension is larger, 1600. Now the context length is larger, 1024. And, compared to BERT, this is, maybe 4 times as big, 1.5 billion parameters. So they used a larger training set too. OpenAI made their own training set, WebText. I don't think it's public. Couldn't find much information about it. 40 gigabytes of text from 8 million documents. And so it's interesting what they did. They looked at Reddit posts, 45 million Reddit posts, but these were Reddit posts that were upvoted at least 3 times to get rid of bad ones. They wanted more respected Reddit posts. And then they looked at the documents linked from those posts. And now the compute cost went from 6 up to 28. Sorry, what's happening here? Okay, from 6 to 28, and the price is back up to 50,000. Okay, so that was GPT-2. Any questions on that one? All right, so GPT-3, this is May 2020, and this was the one that made the really big splash with ChatGPT and so on, although it was later in the year, in the fall. And this one, again, has a similar architecture to GPT-2. It's just bigger. They just took the same idea, made it bigger and bigger. So now we have 96 transformer blocks. We have 96 attention heads per block. The embedding dimension is much bigger, 12,000. Context length is doubled again. And now we've gone from, 1.5 billion to 175 billion parameters. So things are getting really big. Pre-training use a variety of sources. Common Crawl, which is basically looking at the entire internet. 41 different views of the entire internet. WebText 2 different book collections, English language Wikipedia, so in total 800 billion tokens. Pre-training is now gone from 28 petaflop second days to 3.6 thousand. And the training cost went up somewhere, it's not known, but somewhere between 5 and 15 million. To do this, Microsoft had to build them a big supercomputer that had 10,000 of, at the time, the latest and greatest NVIDIA chip, the V100. So if you would have done this on a single V100, it would have taken 355 years to train. But they were able to do it, I think, in roughly a month or so with all these V100s. Okay, so, and this is the one that really got into the press. All right, any questions? Okay, so GPT-4, more recent, March 2023. So now there actually are some innovations. So one of the things that's new is that instead of just making the model bigger, which wasn't working anymore, they use this thing called mixture of experts, where they train a bunch of models. It's not known how many, but it's thought to be 16, and they're called experts. And each of these experts is basically like a GPT-3. Maybe it's a little bit bigger, but it's kind of, on that scale. And these different experts have different expertises. And when you when you give it a query, it will find the expert to serve you. So that's sort of how it works. And again, this is not public, so people have been trying to figure out the architecture and so on. So it seems like they use 120 transformer blocks. This is per expert, context length 8192, 111 billion parameters for a total over all those experts of 1.8 trillion parameters. And nobody knows what the data is, but seems to be about 13 trillion tokens. Now they were using a lot of code as well, computer code. And now the training cost went from 3.6 up to 3.6K up to 230K, or the training compute. And now we have a better GPU, the A100. At the time, that was the state of the art. And we have 25,000 of them, so 100 days and about $70 million. So that's GPT-4. Any questions on that? Yeah.
The experts in a sense, is it like for different domains of questions or queries? Is it?
Kind of, yeah. I don't think I don't know, I haven't read very deeply into this, but I don't think it's like they trained and they said this expert will handle this and that. I think it's kind of like they trained and the experts sort of naturally learned to partition knowledge in a certain way. Based on the way they were incentivized during training, they learned to be different from one another and complementary to each other. And they had to balance them because I think one issue is like they find that one of these experts takes like almost all the queries, and so they had to kind of somehow figure out ways to prevent that so that it was more balanced among the experts. Yeah.
Is this like the idea of model in assembly?
Is it on? Yeah, that's a good question. So mixture of experts is actually an older idea, and the traditional mixture of experts is a form of ensembling, but according to the Wikipedia page, which is linked here, the mixture of experts used for these LLMs is a bit different. And it's more like selecting a particular expert rather than ensembling several. So it's different in that sense, and this Wikipedia page explains all the differences. Yeah. Okay. All right. Any questions? Okay. So this is the other slide I added just this afternoon. So these are just more recent GPTs from OpenAI in chronological order. And there may even be some other ones that I missed. But so GPT-4o was introduced in December 2023. And like not a lot is known about these models. They're not public. So I don't know. Yeah, I don't know much about them. I didn't try hard to find everything about them, but this is what seems to be known about them. So the tokens, number of tokens, has gone from, let's see, the context length has gone from, let's see, GPT was 2K. Here, it was 8K in GPT-4. And so now we're talking 128K, so much longer context. And context is now thought of as being like the most important thing because it's sort of, you really need a lot of tokens to understand a very complex query. So this model, somehow it only cost $10 million to train, supposedly. And then there's another one in September 2024, last fall, that is called OpenAI 01. And this actually this is a different kind of model that uses something called chain of thought reasoning, where when you ask it a question, it does not give you an immediate answer. It actually tries to break that question up into different stages and tries to it's almost like introspection. It tries to understand how it's thinking about thinking. So it deliberates with itself and so on. And then you may have seen this in some of the like pro-level queries. It breaks the problem up into parts. It takes a little longer to get an answer, but then it's a more detailed and an answer that is maybe more accurate. So anyway, so this chain of thought reasoning, I don't think OpenAI is the first. I don't think they invented it. I think Google may have invented it. But anyway, this is what was used in this model. And then in this February, we have GPT 4.5. Now, this is not a chain of thought reasoning model, and supposedly this is like the last one they're ever going to train that's not chain of thought. And they went all out on this and spent $400 million to train it. And so this is like some just gigantic model, context length of 128K, as you can see. So this one I'm not sure exactly what the context length is. I read that if you use 128K tokens at the input, then you have no space for the output. So somehow like the input and output must be at most 128K together. But I think this one actually gives you 128K input context length. Anyway, so one significant thing about this is it passed the Turing test. The Turing test was a test that was kind of posed by Alan Turing, I think back in the 40s. He was thinking about intelligence and machine intelligence, and he basically said, the ultimate test for machine intelligence is if you have a human expert that is reading a conversation between two entities, one human, one non-human, one machine. And if the human expert cannot tell which entity is human and which entity is machine, then we've reached this point, of the machine is, at least for conversation, as good as a human. And so apparently I think there's a couple models. I think one of Facebook's models and this one have passed the Turing test. So that's a pretty big milestone. So the advantage of this style model is you get an instant response, whereas the chain of thought, you don't get that instant response. So I think in terms of like language, chatbots and stuff, I think this would have an advantage because it's not going to like think to answer. It's just going to give you an answer immediately. Okay, and then 2 days ago, GPT 4.1 was introduced, and the main thing that that people are kind of emphasizing about this is a context length of 1 million tokens. So pretty massive. And for some reason, this only costs $20 to $80 million to train, so not as much as this. So that's kind of the progress for OpenAI, and I mentioned that BERT model from Google. And then here's just a list of a few other kind of famous models. So like Google has had actually its own series of models. They keep changing the name, which I don't think has benefited them too much, but Lambda, then Palm, then Bard, now it's called Gemini. And so they're still working in this space. They're trying to outdo OpenAI. And then Meta has its own series, Llama models. And then Anthropic has this Claude series of models. And then, of course, there's smaller companies too, like DeepSeek. They've been generating models, but their latest one from, I think it was January, made a big splash, being a lot cheaper to train, but they were also building on a lot of tricks that people have developed before them, and they did some distillation too, which means distillation is where you take one expensive model and then one network that's expensive, and then you train a simplified model to copy that. And you can kind of distill this complex network into a simpler one. And so that was one of the many tricks they learned. But yeah, they had some really nice tricks, and they showed it's possible to train these models without spending $400 million on them. So, and those are LLMs. And then I also mentioned there's these text-to-image models you may have heard of. So these, you give it a text prompt, and then it generates an image. Some of the famous ones are Midjourney, Stable Diffusion. OpenAI has its own series, DALL-E, and now inside GPT 4.0, you can do this as well. Google has its own image gen series. And there's other ones too, but these are some of the more famous ones. All right. Any question on any of these more recent things? Okay. All right. And then just if you want to know more, so I really like this blog here. This is actually where all the early slides in this lecture packet were basically stolen from, and the pictures were stolen from this blog. I thought he did a really nice job of explaining things. But if he has all nice text there too, explaining things. And he also has Python code, not even PyTorch, but Python code that builds the self-attention, the transformers and everything. And he trains it on next character prediction. And if you want to run it, you can run his code and play with it and stuff. So I really liked that. This is a book that somewhere, it's free. I found this linked on the internet, and I thought that they did a pretty good job of explaining the ideas. This book here is on our syllabus, is one of the optional ones. This is a kind of a much bigger book. It has a lot more details about just all the different topics. It also has code in various, like in PyTorch and TensorFlow and JAX, something else for everything. Although it's, I don't know, it's maybe not quite as easy to read, but these are all good references. There's a whole free course on Hugging Face on large language models. Looks pretty good. And there's a blog I found that does a really nice job of getting into the details of more recent advances in transformer architectures beyond what I described. And these are just a few sources. There's lots of other sources, of course, but I think these are all pretty good. And just one note is, like in our class and in most sources that I've seen until now, vectors are always column vectors. It's just the assumption, vectors are column vectors. But in all the transformer literature, vectors are always row vectors. So just keep that in mind. For some reason, they want everything to be row vectors, so you always have the vectors to the left of a matrix. Okay, so that's all I have prepared. Any questions on anything? Okay, so before you go, I just wanted to complete my attendance roster. So there's just a few people that some people I have 5 different attendance records for. So basically every time I returned a midterm, that was an easy way for me to tell who was here based on who picked up their midterm or not. So 3 were from that, and then 2 more. Some people I have 2 others, and some people I have 1. So let me just go through, and if you're here, please raise your hand. So Lucas Caret Delgado Pinheiro? No? What about Yida Chen? No. What about Jiyuan Chen? Great. Bruce Cheng? Okay. Peyton Groilich? Okay. What about Jake Groh? All right. Eason? Great. Fayaz Jamil? Okay. Declan Johnson? All right. Zebang Lee? Andrew Lin? Ethan Lawrence? Alex Lucas? Camden Majors? Connor McKenna? Spond Mehta? Evan Menges? Grant Merka? Clayton Moeller? All right. Zachary Plotkin? Ling Hao Tian? Josh Wolf? Last name XU? Okay. Jiao Yuan? No. Chipeng Zhu, ZHOU? Okay, so then I have 5 marks for everyone. All right. So hope you guys enjoyed the course. If you have any questions on anything about the projects, you can come up and talk to me now. I'll also be available tomorrow over Zoom. And what else? So if the SEI form I'm using is different, it's some pilot of some new way of collecting feedback, but it would be nice if you give the feedback, because I'd like to know what you liked and disliked about the course and how it can be improved for the future. So please let me know. Otherwise, good luck on your projects, and good luck and have a great summer. See you guys later.
Project, big rating. So say I get like top 5 on the leaderboard for linear, and then my group member gets the lowest score on tree or neural network, and I didn't like we did them individually. Is my grade based on like their last place in leaderboard, or just my linear?
No, your grade is based on your linear Kaggle score, your linear design, and your 5 pages of the 15-page report.
Right. Okay.
So nothing to do with
Okay.
them.
Perfect.
Yeah.
That relieves. That
Okay.
brings a little bit of relief. Right. Thank
Okay, cool.
So I've been, I don't know if I've been doing the most efficient method, but I had the #1 score for like a week or two until yesterday. Then I saw 2 teams pass me, and I spent like 30 minutes, and I took back second place at least. But then, because pretty much for the past couple of days, I haven't touched my best model in a while, and I did a little bit yesterday, but I just have been going back and working on like logistic, because I'm just trying to get stuff to write for the report.
Okay.
It's kind of sloppy,
I mean,
like how I've been testing.
It sounds like
everything.
your Kaggle score is really good, so don't feel like you need to win.
Well, that's why I started working on
Yeah.
my old models again, because I was like, I want to get some stuff down for the report. So pretty much I mean, I don't know if this has been the most effective way to do it, but I've just pretty much been changing I have all these commented, but I'll test one at a time, and then
Yeah, so in the report, I kind of want to hear your thinking process, and I want you to I'm not so much interested in lists of numbers, things that show me that you understand this is a good way to go, you kind of tried to tune this parameter and you made a grid and you found this is the minimum. So
yeah, I mean, I think that's what I was gonna do to tune the parameters. I was gonna choose based off my accuracies. I was gonna go based off my best model, and then I don't know where it landed. I don't know if you saw it, but I had the little line. Oh yeah, that. I was gonna do something like that because I haven't ran this in a while, so I don't know which standardization I used and But I was gonna show something like this that showed the chart and maybe adjust the grid so it's more refined. But then so far what I have, I mentioned here, I made a title page, which I don't know. That doesn't have to count as one of the 15, right? And then pretty much I was gonna make a logistic regression and then an SVM section. So I was starting on the logistic regression. I pretty much, like I said, I've been writing all these down in a Word document because it's not saving since I keep uncommenting stuff and changing it. So it's just a good way to keep track. But then pretty much the general paragraph was just saying I've been testing. I was having issues with the Saga and SOG solvers, so I just scrapped those because no matter what I changed the max iterations to and the tolerance, it seemed like it just wouldn't converge. So I was I just stuck with these 4 main ones: liblinear, L1, liblinear, L2, and then the 2 main L2 solvers. But pretty much this paragraph, I was just saying I tested these 4 first. Robust scaler was giving me the best accuracies out of all of these, and then pretty much I said I was trying to figure out if there was a good way to visualize the data because it's kind of a mess if you visualize all of it. Because I feel
I don't know of a good way to visualize it.
yeah, because I was just going based off assumption. I was robust scaler is performing the best due to how it handles outliers.
Sure, sounds
And then I
good.
said based off that, I just examine 2 more methods that are good at handling outliers.